So, welcome to DeepSec 2009. This is the second day. This is the Great Writing School room, and next on our program will be Nelson and Haj. I just learned. Nelson and Haj about rebootless injection. So keep your servers running and still be updating the kernel. So I've never tried this. I don't touch these kind of things, but obviously he has. And
it works.
I'm very much looking forward to that. So, Nelson.
All right. Hi, everybody. I'm going to be talking about Ksplice, which, as Sven just said, is a system for rebootless kernel updates. Quick background on myself. I actually just graduated from MIT in June of this year and went straight to work for Ksplice Inc., which is a startup that was founded by a bunch of friends of mine around this Ksplice technology. And so I'm currently one of the lead kernel developers working on the Ksplice software. All right, so we'll open with what is Ksplice? Well, I just told you. It's a system for rebootless kernel updates, which means that I have a running operating system kernel on my machine that's got some bug in it, some behavior I don't want. I can take it to a running kernel without that bug, without disruption, without stopping any programs, without shutting the machine down, without losing any state. Now, people have been doing sort of, assembly hackers especially, have been doing, ad hoc binary patching, do a hex editor on dev kmem or whatever for years. What's really unique about Ksplice and what makes this the first ever truly practical hot update system is that Ksplice is an automated system for taking a traditional source code patch, just a diff file like you would generate from your working tree, and in an almost completely automated fashion, turning that into a rebootless update that can be applied without any disruption or loss of state. All right, so why do you care? You probably already sort of understand, but just we'll run through the reasons. Why do you care about rebootless updates? Well, so you can have your cake and eat it too. You can upgrade promptly and avoid costly reboots. You probably understand why these are good things, but we'll run through a lot of reasons, some of which you may not have thought of. Why is avoiding reboots important? The obvious one is avoiding downtime. When my server's rebooting, it's down. I can't access the services. Anyone who depends on this server, can't do work while it's rebooting. I lose software state. I have running application state, storing things in memory that has to all get reset and reinitialized. This is slow. This is why reboots are slow. And it can sometimes mean extended time to get back up and running while systems rebuild their state. And reboots can cause unexpected problems. Hardware failures, for instance, are much more common at reboot. If things, often sysadmins aren't as good as they should be about configuring things to come back up on reboots. Obviously, this is something you have to solve eventually, but anything that gives you more flexibility to put off these reboots and control when exactly you need downtime to update, it has to be a good thing. All right, so rebooting for updates sucks. Why is it important that we upgrade promptly? You're all security guys, so these numbers won't surprise you. There are 70 to 140 or so bugs fixed in the Linux kernel every month. There's new privilege escalation, CVE, somewhere in Linux roughly every month. Possibly more recently if you've been following Spender's work. And greater than 90% of software attacks anywhere attack known vulnerabilities. So it's the vast majority of attacks aren't 0 days that no one has heard of. It's vulnerabilities that have been heard of, have been patched, fixes have been released, but people were too slow to patch because it was painful, disruptive, didn't want to reboot, didn't want to have to deal with it. And days or weeks are far too long to wait. At MIT, I ran a login server for all of the MIT community. So all of the 10,000 people at MIT have shell access. They're all potentially untrusted users on a Linux server. And we saw multiple occasions where a privilege escalation CVE would get announced, would get mailed to the Linux kernel mailing list, and in under 24 hours, someone was trying to root us. So really, you can't even wait a day to patch these kinds of vulnerabilities. And that's why Ksplice is so important. All right, run through the obligatory cool feature list. It's been backported to kernel 2.6.8 and forward, which means that basically, aside from a very small number of holdouts on the 2.4 kernel, we can patch any running Linux kernel out there. And we mean any kernel, no advanced preparation. This works on an unmodified kernel. You download your kernel from Red Hat or Ubuntu, or you build whatever weirdo kernel you want from source. Ksplice can patch it. Doesn't matter if it was built 4 years ago. We can patch pretty much any code in the kernel. We can patch modules. We can patch parts of the kernel that were written in assembly. We can deal with all of the weird tricks that Linux does. No problem. And there's basically no performance impact. As I mentioned, it doesn't require any advanced preparation. So before you use Ksplice, you're running a completely stock kernel. So there's literally no performance impact. And even once you've updated it, it's negligible. It's basically impossible even to measure it. All right. A lot of people's first reaction to Ksplice is, all right, can I really trust this thing? This is kind of a crazy idea. And the answer is yes. This is actually not a bleedingly new technology. The initial release was over a year ago as open source GPL v2, all of the tools. And my company, Ksplice Inc., was founded a couple months after that and has had 4 and now 6 engineers working on this project full time since June. So this has had a lot of developer effort into it, and we totally trust it, and it shows. We've been using it on those servers at MIT that I mentioned since its release. So over a year now, we've been updating running servers with thousands of users using Ksplice. My company has deployed a early version of our product, which is a rebootless update subscription service where we provide our customers with rebootless updates. There's a free version for Ubuntu Jaunty and Karmic, if you're running those, that's been downloaded and installed on around 10,000 systems. And all of those people are getting rebootless updates from Ksplice. The tools have been improved, and you can apt-get or yum install them on Debian, Ubuntu, and Fedora. And we've proposed it for mainline on the LKML and gotten some review from top kernel developers who seem basically OK with the idea. So although a year is relatively new, this stuff we believe is totally solid. We've been running it on production servers for years. It works. You can trust it. All right. That was a blinding overview of Ksplice. What is the rest of this talk? I'm going to talk about using Ksplice, what the process actually looks like to use Ksplice to patch a kernel. We'll do a bit of a technical deep dive into the crazy things that Ksplice does that let it work, and let it work so sort of magically. We'll talk about what patches require some additional human effort to apply with Ksplice and what that effort looks like. And then I'll just talk a little bit about some other uses we've found for Ksplice and give a quick plug and demo for our product that I just mentioned. So, using Ksplice. Ksplice takes as input 2 source trees. It takes the pre-source tree, the source of the unpatched kernel, and then what we call the post source, the source of the patched kernel. Normally, we give these to Ksplice in the form of a source tree, a git checkout, and a diff file. Creating a Ksplice update, once we've set up our build tree, is as simple as running the ksplice create pan command. We give it a patch file, we give it our Linux tree, and it goes off and does its magic and produces an update tarball. Ksplice updates are given randomly generated unique IDs just to keep track of them, and that tarball contains everything you need to update your kernel. Become root and use the ksplice apply command to apply that tarball to your running kernel, and Ksplice just prints done, and there your kernel is patched. That's literally all it takes. For fun, I'm going to give a quick demo. I'm, in fact, going to patch the laptop, build a Ksplice patch, and apply it to the laptop that I'm giving this talk on. Like I said, I believe this stuff works. Can you read this fine? All right. So I'm going to show off what is my favorite party trick kernel update. I'm patching the function uptime proc show in the Linux kernel. This is the function that returns the value of the current uptime user space. And I've just added 2 lines in there that are going to add a year to my uptime. So I have this patch. I simply run ksplice create. I'm going to give it -j4, which says to use a parallelism of 4 when it's building it. I'm going to tell it to skip the pre-build. That's just going to speed it up for the demo because this tree has already been prepared. Patch equals uptime.diff, and source directory is dot. Ksplice goes off and does a whole bunch of building. It's going to build the pre-tree and the post-tree. It's going to difference them. You see some debug output there. Tells you what changes it's detected. Does some more building, combines some things. And Ksplice update tarball, written to Ksplice and then a random ID. Now, let me try this out. Check my uptime. So this laptop has been up for 9 days. Run the Ksplice apply command. Done. Kernel has been patched. Check my uptime again. And if I decide that I don't really want to lie that way, I can do the Ksplice undo command. Give it the unique ID that Ksplice generated. I can actually do a Ksplice view, and Ksplice shows me this patch. I didn't give it a description, so it doesn't know what it is, but it knows that it's applied. Ksplice undo, pops it right out again, and my uptime is back. All right. All right. So that was the demo. So now that I've shown you how blindingly simple this is to use, let's talk about how it works. So we start out with this. We have our running kernel. It has some symbols in it that we want to patch. Let's say that we want to patch this function foo here. It's buggy for some reason. The basic process is that we load a new kernel module that has a new copy of foo, and we write in a jump to the beginning of the old foo that simply redirects execution to the new foo. Fairly straightforward trick. Assembly hackers have been doing this kind of thing for years. The devil is in the details. So here's the high-level picture of the details. We need to first figure out which code has been changed. We have this source patch. We need to somehow translate that into binary files. We need to resolve symbols in the post code. This code afterwards calls other functions in the kernel, uses other variables in the kernel, and we somehow need to find out where those are located in the running kernel so that it can use the right data. We need to find this function foo in the running kernel, and we need to find a safe time to insert the jump instructions. If we were to scribble over some code while it was being executed, bad things would happen. And I'll talk more about what all these mean later. So, again, high-level picture. We build the update, apply the update, find what changed, and we find out what changed, and we prepare what we call the pre-code and the post-code. Every Ksplice update actually includes both a copy of the original source and of the binary built from the original source, except that it's been modified in some very important ways that help us do the patch, as well as a copy of the post code, the code built from the patched source that, again, has been modified in similar ways. And then at update time, we actually match this pre-code to the running kernel. So the binary code that we built that's supposed to be the same as the running kernel, we actually go through and match that instruction for instruction with what's in the running kernel, both as a sanity check and for some very other important reasons. And it finds a safe time, it inserts that jump instruction. So the process of building an update. We start out with the pre-source and the post-source. We compile them both using GCC with some special options that I'll mention, but essentially just the same way you would do a normal kernel build. And we get the compiled pre and the compiled post source. We then diff those at the object code level. We have a tool that goes in and actually reads all of the .o files and compares them. This is very important. You can't do the diff at the source code because of issues like inlining, for instance. If I patch a function, who knows where GCC might have inlined that function, copied its code elsewhere? There is no way, literally no way, to have that information from the pre-source. Working at the object code level also enables us to handle assembly and C source in exactly the same way, because they both turn into the same object code. Then, from this object code, we apply another tool from the Ksplice toolkit that uses libbfd, which is the same library used by GCC and the linker to parse the object files and modify them to produce the pre and post code bundle. So in order to understand what way we modify them, I'm going to have to briefly delve into how C compilers and linkers work. This should hopefully be familiar to many of you, but everything you should need to know should be on this slide. So here we have a trivial C function that increments some variables for God knows what reason. But there's two kinds of variables here. The int y is declared within the same compilation unit, which means that that y refers to a variable that is compiled at the same time. Whereas the extern int x means that we're referencing some variable outside the compilation unit. So at the time that we compile foo, we don't know where x is located. We're not going to find that out until we link foo.o with whatever piece of code compiles x. And so the way that works is that when the compiler compiles that y++, it generates a entry for y somewhere in the same binary, and it just points that y straight at that entry. It knows where it is. When it compiles the x, it puts an entry in the symbol table for that binary that says x is an undefined symbol. Its value will be resolved later. And then at the point where it compiles x++, it puts an annotation that says, when you link it, fill in the value of x right here. Now, this picture here isn't what we want if we want to try to hook foo into the running kernel, right? If I want to hook foo into the running kernel, I don't want foo to get a new variable y, right? I need it to point at whatever variable y was previously present in the kernel. And so the primary modification that we do with our tool to extract the pre and post code is we actually remove all defined relocations from the binary. We, in a sense, do a reverse link and remove all variables that have been linked to point to undefined variables that will get linked at apply time in the kernel with whatever symbols are actually present in the running kernel. All right? And then we can strip the y from our binary because we don't need it. We're just trying to replace foo in this hypothetical example. And so we don't need to load it. We don't need to take that memory. All right, so quick summary of building an update. An update contains the pre-code and the post-code, the source that's been modified, like I just said, of the original objects and the post objects, as well as a list of functions that have been changed, which functions it's supposed to insert trampolines jumps into. And the major modification, like I said, is that all symbols have been unresolved. These binaries have no resolved symbols. They need to be completely linked at runtime. All right, so that's how we build an update. How do we apply an update? So the first thing we do when we're applying an update is we take that pre-code, the compiled pre-source, and we do this byte-by-byte check that I've talked about. This is a safety check. It lets us verify at runtime that the code we're patching is exactly the code we think we're patching. Obviously, in theory, this should never fail if I'm not incompetent and I built it against the right source, but it gives us a very powerful guarantee that what we think is happening is in fact what's going on. And it has enabled us to catch thousands of bugs that would have otherwise oopsed our kernel. And we actually, when we're matching the pre-code, we use this to discover the values of unknown symbols in the kernel. I'll talk a little bit more about how that works. We then do the actual apply using a Linux kernel function called stop machine, which grabs exclusive control of every processor on the machine, stops the world, and hands over execution to us. We perform a safe time check, which basically amounts to making sure that the code we're trying to patch isn't currently running. And we insert the jump instructions. Now, this stop machine that I mentioned, in order for this to be safe, we have to use the stop machine, which stops every processor on the machine, stops all processes except for us, and gives us exclusive control. This sounds kind of expensive, and it is a fairly heavyweight mechanism, but it's not too bad. It takes less than 0.7 milliseconds, which is a long time on the order of a computer, but for anything other than sort of real-time systems, it's pretty acceptable, especially compared to rebooting the entire machine. All right, so now I'm going to dive a little bit more deeply into this matching of the pre-code. Like I said, it's a byte by byte or instruction by instruction comparison. And when the obsolete code, the pre-code, refers to a symbol, we discover that symbol value based on the running kernel. So remember how we unlinked all of this object code. We replaced every reference to an undefined symbol. So that means that when we have the pre-code, we can actually backsolve for the value of the symbol. And when we use these discovered symbols, we use them to resolve the postcode. And there's a lot of grody details because the Linux does some really weird things that we have to be aware of. So let's talk about this resolving of symbols in the running kernel. So this is some foo prime. This is the patched foo that we're trying to load. So it references some symbol that we'll call bar that we need to find in the running kernel. So the obvious first candidate to find this symbol bar is to use the kernel symbol tables, right? You know, the symbol table, the module loader symbol table, or proc k all syms. There's a couple of reasons why that doesn't work. The most difficult one, though, is the problem of static local variables in C. If you're familiar with the static keyword, it creates a variable that's scoped to either the scope of a function or the scope of a compilation unit, but that's long-lived. Now, because they're locally scoped, there can be many variables that have the exact same name, but live at different places in different addresses in the kernel. And we'd really like to be able to patch code that uses these variables, because they're everywhere in Linux. But we can't find their value in any symbol table because they're not exported, they're not global symbols. And so this is the real motivation for this crazy trick that we're about to talk about. So instead of trying to look up bar in some symbol table, instead what we do is we find any function x that was compiled in the same scope as foo. This could be the original function foo, or it could be some other function in the case, say, where the original foo didn't reference bar, but the new foo had to reference bar. So this is in the pre-code. And then somewhere in the kernel's running code, at some fixed address, because it's been loaded into memory, is that same function x. And so what we can actually do is when we're comparing those, when we encounter that symbolic value bar on the left, we know what value is at that address there, and we actually do the reverse of what the linker would do. The linker would subtract some numbers and add some offsets. We add this is a relative offset to that foo, and then the -4 is an oddity of the way x86 linking works. And we backsolve to find what the correct value of bar is. No symbol table at all. The really cool thing, we can actually patch kernels that were built without any symbols, that don't support symbols at all, don't have a symbol table, don't have a proc k all syms. Because once we've found one function, that function calls other functions. We can find those functions' addresses using the same trick and flood fill outward to find every function that we care about in the running kernel. And now once we have that bar, we can use it to link this function foo prime. We can do the reverse of this reverse linking, so which is just linking symbol resolution, and we get a foo prime that we're ready to patch. So that's the first stage of application, is that we do this run pre-check, we call it. We extract these symbol values, and we use those to relocate the post code to be ready for application in the new kernel. The next step is this safe time check. We have to find a safe time to replace these jump instructions. Now, the point here is ensure that switchover to the new code version is atomic. And this is atomic in a couple of senses. The most obvious thing, perhaps, that could go wrong is if we overwrite code that another CPU is executing as it's executing it, basically arbitrarily weird shit could happen. Another concern, though, is it may not even be safe to have the old code and the new code running at the same time. Let's say that the patched code changes the locking conventions. It changes how some variable is locked. And the old code has some different convention. It flips lock ordering or something. If the pre-code and the post-code are running at the same time in different threads, we could well get a deadlock in that situation. If they changed how the semantics of data, we could get something worse. We could get subtle data corruption. And subtle data corruption is your absolute enemy when you're building this kind of system, because it will take forever to debug, and it will be sitting there running on people's machines, silently destroying their data for months before you notice. So we not only need to check that no code is executing on the jump instructions, we need to check that no code is executing anywhere in any of the code that we want to patch. Now, if you're familiar with assembly hacking, sort of the way debuggers pull out stack traces, the usual way you pull out a stack trace is by using the frame pointers, which are registers saved according to a calling convention. That actually gives you a very nice stack trace you can follow back. So we might imagine that we could follow this stack trace, figure out where every function is, and be good. However, of course, just to spite us, Linux tends to build without frame pointers, which means that the stack is just a whole mess of data. And so what we actually have to do is for every thread, in order to check that the stack is not in the middle of executing any replace function, we actually do a conservative check. We simply check every word on the program stack from wherever it is to the base and see if any of them point to the code that we're trying to patch. This can, in principle, have false positives if there's garbage data or whatever on the stack, but it's pretty much guaranteed to assure us that no one is patching no one is in the middle of executing anything that we're trying to replace. If this check fails, we abort the apply and try again in a couple of seconds. For most patches, this turns out to be relatively rare because the typical security patches end up being in some unused code path, or rarely used code path. That's why no one caught the bug. And so most of the time, this doesn't happen. If it does happen, usually by trying again a couple of times, you can fix it. And in extreme cases, we've seen situations where you need to stop Apache for 5 seconds in order to apply a patch, which is a little unfortunate, and we're trying to work on some tricks to make that less frequently necessary, but it's still way superior to rebooting the entire machine. All right. So that is the process of building and applying an update. So now the question is, what patches do we require a programmer to do new development in order to apply them? Now, if you paid attention to what I said, you sort of thinking about the possible problems here, we're only changing code. We can't automatically transform data because the data is not, in general, going to be the same data that it was originally built as. It's going to have evolved somehow over the course of the execution of the program. And so we simply can't do the same kind of automatic transformation for data. Some examples of things that happen relatively frequently, or at least potentially frequently, that you might want to do is, if I add a new field to some struct, then all kinds of things go bad if you just tried to apply the patch without any updates. More subtly, if I change how a data structure is initialized, let's say that I'm some network server, and when a client first connects, I set their credentials in some way. If the code that sets their credentials is incorrect, then even after I apply the Ksplice update, any existing client might have incorrect state that has the wrong credentials attributed to them, and the machine is potentially still vulnerable. Fortunately, these kinds of problems are relatively rare. We did a study of every CVE announced for the Linux kernel in the 2005 to 2008 period that was of a severity higher than denial of service. This is not because we don't care about denial of service bugs, but because we do think generally they're less worrisome than privilege escalation, and there are just a crapload of them, and we didn't really have the time or energy to track down and analyze all of them. But of all of the CVEs in 2005 to 2008 affecting the Linux kernel worse than denial of service, this is the list of CVEs that apply unmodified with Ksplice without writing any new code. This is the list of ones that did need new code and how many lines of code we had to write. For those of you who weren't counting, that's 88% of this list can be applied with no new code, and 100% of them we were able to apply after writing a little bit of code to modify state and update the kernel to the new running data structures. All right, so what does this new code, ranging from 1 to 50 lines in these cases, do? The most common thing for our code to do is that we need to walk existing data structure instances. Usually sort of the structures you care about are stored in some linked list somewhere in the kernel, and we can walk through all of them, updating them in some way. Because of the run pre-matching that I've mentioned, using the exact same technique we used for the post code, we have access to any symbol in the kernel, not just the exported symbols. So even if the state that's corrupt is deep somewhere in the internals of a module, it doesn't matter. We can access it quite easily. If we're adding a new field to a struct, we need to give that field the correct initial value for existing instances of the struct. This is sort of sometimes the trickiest part of these transformers is figuring out this field that was supposed to have been initialized at some point in the past. What would its value be at present if this bug were not present? That sort of is the thing that requires a kernel hacker or a couple of kernel hackers reading and really understanding the code to figure out how this initialization needs to work. Fortunately, it's fairly rare. So what does this form of this new code look like? Some sort of previous research systems have adopted the solution of sort of having some ad hoc language that describes these data structure transformations, some domain-specific language that describes translation. We have a much simpler approach. The code is simply more C code that you drop into the patch that is applied exactly like all of the other code. And there are a couple of macros that you can call that indicate to Ksplice at various points during the update process, call this hook that I've embedded, perform this modification that I've put in there. For instance, there's Ksplice pre-apply. This happens after the run pre-matching stage, so when we have all of the symbols, but before the stop machine stage. So because it's happening before, it's allowed to potentially sleep. It's running in process context, user context, if you're familiar with Linux kernel. So it's very flexible, but it's not guaranteed to be atomic with the update because there's some time that passes between it and the stop machine. There's a Ksplice apply hook that actually happens inside stop machine when the machine is paused for the update that can do transformations that need to be atomic with the application of the code. There's hooks for if the update fails, there's hooks for after it applies, and then there's the same set of hooks for backing out the update. So let's look at an example of a CVE patch that we've looked at that needs this kind of transformer. This is the sort of first example I talked to. This is a patch, CVE 2006-1056, that had to do with the initialization of this capability bit on AMD processors of a certain generation. So this is a bit that tells the Linux kernel that the fx save instruction on this processor architecture leaks some information in some way, leaves information around that the kernel needs to clean up, or else it risks leaking FPU state from one process to another, which could be the cause of any kind of fun side channel attacks on crypto engines or whatever. And now, if you look at this code, you'll see that __init annotation. If you're a Linux kernel programmer, you'll know what that means. That means that this code is run at boot time and then literally thrown away after the boot is over. So I can't patch this code at runtime because the code isn't even there anymore. And even if it was, it wouldn't do me any good because it's never going to be called again. So what we have to do is write some code that walks all of the processors in the system, checks if they are the appropriate type, and sets this bit. And that's what the code looks like. The bits in blue are the ones that came straight from the previous patch. The bits in black are the new code that we had to write. We write this new function, set fxsave leak bit, and it walks over every CPU in the system. It checks if the x86 level is greater than or equal to 6, and if it's an AMD CPU, and if so, it sets that same bit. So it simulates the effect of this code having been patched at runtime. and then we simply insert a call to Ksplice apply that tells the Ksplice runtime, run this code inside stop machine during the patch. If we wanted it to be completely thorough and make sure that this patch could be undone cleanly, we would need to write the reverse code and do a Ksplice undo that undid it afterwards. In this case, because it's some bit that no one will understand, it's probably harmless, but it's sort of always good to clean up after ourselves. I'm only showing this because the reverse is trivially the same and would be kind of boring. All right, so that deals with the problem of changing the initialization of data structures that were already there. A slightly trickier problem is, what do I do if I have a patch that looks like this? I'm adding a field to a struct. And you know, I have some array of this struct, or I have some structs that are already allocated in memory that are long-lived, that are going to live before and after this patch is applied. Now, if you know basically anything about C, you're probably going to see the problem here. Previously, the code looked like this in memory. There was 4 bytes, you know, for this foo. There was 3 structs in a row. Each struct was 4 bytes, had some value A in it. In the post code, the layout's going to look like this. Now, I don't really see a good way to transform the old code to the new code, especially not in place, because we can't simply expand it. There might be other things after foo. We could maybe imagine changing where foo is located, copying the values over, and patching every piece of code that possibly touched foo in the running kernel. We could maybe imagine doing this. It would be unpleasant. What if instead of this random struct foo, this was struct task struct, the struct that holds the representation of a process in the Linux kernel? We've written patches that patch that. I don't really want to be in the business of having to find and patch every last function in Linux that touches a process. We might be able to do it in principle, but it would be pretty unpleasant. So instead, what we really want to do is maintain the old layout in place. And we do that, yeah, question mark, to say, how the hell do you do this? And the answer is we don't. We dodge the issue. We use a technique called shadow hashing, which is actually mentioned in the research previously for this purpose and is used for some other purposes. We store this shadow field off to one side. All of these B fields, we're going to store them in some other structure separately allocated somewhere. And when we need to access them, we look them up by hashing the address of the structure and looking it up in a hash table that contains all of the values of B's. This is a hash table. It's order 1 time if you remember your freshman algorithms class. But the other cool thing about this is that if we think about this, what do we have to do this shadow lookup for? We have to do this for any fields that we've added. By definition, fields that we've added are only going to be referenced inside the patch that we're already dealing with. So it's very, very easy to find and update every location of code in this patch that has to deal with this. So if we have an old instance of struct foo at address 0xbeef, we simply look up in a hash table, we hash that somehow and follow our hash table, and we find we have a hash table for the values of B's. And that gives us the value of B for that struct foo. And so that's how we can manage to do these updates where we're changing the shape of data structures in place without having to modify every last bit of code in the kernel. All right. So that is the spiel on how Ksplice works. I'm going to talk briefly about another use that somewhat surprised us, but then rapidly realized was really cool for Ksplice, which was Ksplice as a debugging tool. So I have this running kernel. It has a bug. Somehow some data is getting set incorrectly, or it has some kind of bug. What I would really like to do is look inside that kernel and track what's going on. And there are tools. I could use KGDB. I could pull up a serial console or something and attach to the kernel. System tap gives me a certain set of points I can inspect. Or what I could do is I could write a new version of the function that had debugging statements every line and Ksplice it in over the old function. This might seem like a bit of a heavyweight hammer to get debugging information, but there are actually reasons that we've found it to be a lot easier than using these existing tools. One, it's real C. I can write C code exactly like I would write in the kernel if I were to recompile and rebuild. I don't have to deal with GDB, which, while a wonderful tool, it doesn't just quite give me the ability to just plop down C and run it there. I can insert code basically anywhere in the kernel. Again, like I've mentioned, this run pre-matching gives me access to static variables, local variables, whatever. And so things like system tap have sort of some set number of hook points that you're allowed to hook into the kernel at. We have no limitations. We can replace any bloody code we want. Find any symbol value, like I mentioned. And the one that I really love is we work on a completely unmodified, unset up original kernel. So, oh crap, I forgot to configure KGDB in my debugging kernel. Doesn't matter. I don't have config system tap or config ftrace, or I don't even know which config options that depends on offhand. I have no idea whether or not my distro kernel that I'm working with or my kernel enables them. Ksplice doesn't matter. Any kernel, it's running kernel, there's some bug, I want to track it down, bam, just plop in the Ksplice code. And so I've actually found this to be, even when debugging Ksplice itself sometimes, I'll have some problem, I'll Ksplice in a new update that looks at the Ksplice core and, prints more debugging information or whatever. So yeah, I find this totally useful. All right. Now I'm going to give a brief spiel for what my company, Ksplice, is working on now, and a brief demo because it's cool. We're working on a product. What we're trying to do with this technology is our vision is that basically all updates should be rebootless. You should never have to reboot your computer, your router, your database, your web server, your SAN, anything ever for security updates. They should all be able to be applied rebootlessly. And we're working on making that vision a reality. Our current product is Ksplice Uptrack, is built around this exact same technology that I've just told you, is a subscription service of rebootless updates. You install our client software, and it downloads a feed of rebootless updates for all of the CVEs, all of the security problems, and serious bug fixes announced in your distribution, and applies them rebootlessly. So we build the updates, you just click a button, and your kernel is up to date. Let's see if I got this one. All right. So I have here inside of VMware VM, this is a stock install of Ubuntu Jaunty. So this is using the stock kernel that was released 6 months ago. If any of you have been paying attention to, well, the internet, you probably know that there have been a lot of problems in Linux since then. And so normally I wouldn't really want to be running this 6-month-old kernel. But I'm running Ksplice Uptrack on here, and it has this little K icon up here with an exclamation point. It tells me I'm up to date. It tells me I'm out of date. And I can, in fact, see exactly how out of date I am. Remote buffer overflows, local privilege escalation in SOC send page. Who remembers that one? I just click a button. It'll prompt me for my password. And every time that bar moves forward, it's applying a Ksplice update and fixing a problem in my kernel. I don't really think it could get any easier than that. And it even takes care of details like if there's an update to a module that you don't have loaded, it patches the module on disk so that if you load it in the future, you'll get the updated version. And there, done. No more SOC send page. So the Ksplice Uptrack is available completely free for Ubuntu Jaunty or Karmic. If you run those on your laptop, you can head to ksplice.com and download them right now and get kernel security updates at the click of a button. And we're offering it for enterprise distributions. It's a service that we offer. You can come to contact us for availability. All right, so that's Ksplice. Some quick thanks. Jeff Arnold, first name on this list, is the inventor of Ksplice, a good friend of mine from MIT. He did it as his master's thesis. So all of the crazy, crazy, brilliant ideas that make it work are mostly his. And the rest of the Ksplice team there is the guys that I work with making this stuff better every day. All right. For more information, or see our website at ksplice.com, or feel free to email me with any questions, comments, questions about the talk, comments on the talk, questions about Ksplice, whatever. I'll be around for the rest of the day and tomorrow if you want to find me in person and talk about something. And so I think we have a couple of minutes left for questions.
2 minutes left, actually, but...
Oh, right. It's 50 minutes, not...
Any questions? How big are the updates? Can you repeat the question?
I can just repeat it. The question was how big these update tarballs are. It varies depending on how much code you're trying to patch, but they're usually, I think, on the order of 10 to 100K. Anyone else?
Yep.
Hi. What happens when you reboot the system? After you have updated, then you have used Ksplice?
I mean, nothing special happens when you reboot the system. The question was what happens when you reboot the system after applying Ksplice updates? I mean, nothing special happens. The Ksplice updates go away. You can choose to boot into, a new kernel that's already patched, or if you boot into the old kernel, Ksplice itself doesn't automatically apply the updates, but actually our uptrack system, the management system, has an option to, at boot, automatically apply all of the Ksplice updates you previously had applied, so that you can get back in the exact same state you were before you rebooted.
Any questions? Anyone?
All right, I'll be around for the rest of the day. I'll be at the party tonight, and I'm actually here tomorrow. Probably, I think there's a brunch that I'll be at if you have any questions or want to talk. Thank you.
Thank you.